was like, I don't know. Click and figure it out. So yeah, I'm titled from now on. So this one I titled Joint Densities and Covariance. So we won't do much covariance, just a little dabble. That's it, if we get to it at all. Okay, but anyway, so there's our rule for independence. Two things are independent if the probability of the product, that's one of the ways you can check to see if two events are independent. And then density functions. So now we have x and y are independent if having one of them happen doesn't affect the other. That's basically what this is saying, is that one of them doesn't affect the other. So the way that this looks in joint density function land is that the joint density function will be the product of the marginal densities. And marginal densities are just, this is the density function, the probabilities for x if we ignore y, and this is the probabilities for y if we don't care about x. So anyway, I did my math here so that we could speed things along just in case we have questions. But here's my work for this first one, and I haven't got my answers because I thought we could figure out the answers. So a little bit of annoyance here with integration by parts. No. Here's the integration by parts. This one wasn't bad. The main thing you had to remember is algebraically e to the negative x plus y is e to the negative x times. Hey, welcome. Oh, looking even better than me. I need to look that good. Pocket square and everything. That's impressive. Okay, but anyway, so you need to know that algebra that we have there. So that's the first deal. If you didn't know the algebra.
Were we supposed to integrate, but didn't it just ask if it's independent?
Yeah, it asked if it's independent. So how do you know if it's independent?
So are they separable?
Oh, that you can separate it into a product?
Yeah.
I guess I don't trust that.
Why?
Because of the second part.
What's the second part?
This one. That's not independent.
Why is it not independent?
We'll see. So that's a trick. So the trick, maybe I should mention, when does that trick work? So the trick is that if you can separate your random or your density function into a product, and you can completely separate it into x's and y's, product of x's and y's, it's usually going to be independent. But that's not a surefire way to check. The reason why it's only usually is because it depends upon this stuff here. Notice that these, as long as the domain, so here the domain is all of the x's bigger than 0, all of the y's bigger than 0, as long as the domain is square or rectangular. And I know that's not, you don't think of that as a rectangle, but it is. It's just an infinitely large rectangle.
Why couldn't we say the second one isn't independent because the x is less than the y, so then we know it can't be?
Well,
So why would we have to do work for that?
I'm going to do work because I want to. Okay.
But is that like a fair estimation to be like that's not independent because you have?
Yeah. So well, here's let me finish here. So if you have a product, if you can factor. So if you factor, then it works as long as you have a rectangular region. So triangular regions, and once again, I'm not going to trust. Well, okay, it is a triangular region, and that's why it isn't independent, I guess. But the true reason it isn't independent is because of this. In both cases, this one is independent because I can take the density function and write it as a product of two density functions. So if you didn't do this, I guess it's fine, but I'm doing it. So I'm gonna do it just because I want the marginal density functions. So anyway, yeah, this one is marginal density function for x. This is marginal density function for y. The product of those two is this there. So that's why that's independent. Yeah, I guess technically. So let me walk it back. Technically, you don't have to do this. I'm relying on the definition of independent random variables. You're probably relying on some sort of a theorem. that is based on this definition. Some sort of theorem that says that if you have two independent random variables, then you'll be able to factor this. Certainly, if I couldn't factor that, then you wouldn't have independent random variables, because otherwise, yeah. So I'm just a little distrustful of especially this, because I think I could come up with two independent random variables on a triangular region. Now I'm going to have to do that. I better put my money where my mouth is, but I can't do it right in front of you, so I'll have to think about this. So let's see. What I want to do is to show you that, here we go. I'll just put this as my homework, is find two independent random variables on a triangle. I'm not convinced that you can't. So just because it's a triangular region, I'm not convinced. I'll think about it, but not right now. So anyway, I did do the marginal density functions, even though apparently maybe I didn't have to. For the second part, this is my marginal density function for x. This is my marginal density function for y. If you multiply those together, you certainly don't get 2. So that's why that isn't independent. Okay, so yeah, if you're just going with the product, though, that makes the next one easy, doesn't it? Let me see. Yeah, yeah, because that's not a product. Yeah, 22a, it's not a product, and it's a nice rectangular region. So there you go. But you couldn't do, you'd have to do b. B you'd have to do separate. So I did the marginal density functions anyway. So there's that's marginal density function of x and y. And of course, the product of those does not equal this. So x plus 1/2 times y plus 1/2 doesn't equal x plus y. So that's out the window there. But then in terms of that last, okay, so then in the process, apparently I did that. So that was good. And then finding this, this is what that represents. X plus y is less than 1 is this region right here. So I set up my double integral. I didn't finish it, but that's easy enough, isn't it? Let's see, this is going to be xy plus y squared over 2, evaluated from 0 to x, 0 to 1. So then that's going to be what? X squared plus, so 3/2 x squared, 3x squared over 2, from 0 to 1. And then that's going to be x squared over 4, or x cubed over 6. Oh, duh. X cubed over 2. I don't know why it took me so long. So then that all equals 1/2. So I'm getting 1/2 for that. So the probability of being in that triangle is 1/2. And it.
You get the 3x squared over 2.
So I'm plugging in the limits here. Here, I'll do it over here. X squared plus x squared over 2. Yeah. No, it's a valid question because I've been not doing as well in terms of my math lately for some reason. Yeah, it's simplification. So my mental math, I should say. My mental arithmetic has been failing, it seems, more frequently than it should this semester. It has me worried. But, I can go work at Walmart if I have to, right? Okay, so, oh, we don't need to record anymore, so we don't need, well, too late, it's going. So 22 look okay? Any other further issues with 22? All right, no one's got anything. So let's move on to 23. I think, did I just get it set up? Yeah, I just got it set up. So here again, so independence, okay, so you could factor that. So it's factorable, so it's independent, especially with this sort of a rectangular situation here, the nice square region. So I'll just write this down. 12x 1 minus x times y. So you can separate out the x's and the y's. But I went the distance and figured out the marginal density functions. And when you multiply these together, you get the density function up there. So maybe I did more work than I had to, but I feel good about my work. So, anyway, let's do the expected value of x. That's hopefully easy for you because these are nice polynomials. Expected value of x. I'll just set it up, but if anyone really needs me to, I can actually do the math. So it's x times 12xy times 1 minus x, d whatever. It doesn't matter which order you go in, dy dx, because of this rectangular region. So something like this. So you'll end up with what? 12x squared y minus 12x cubed, and then you have to integrate that. So any issues you guys got that? You can do polynomial integration at least. Okay, last one, and then we can loop back around if we need to. This went quicker than I thought. I guess that yeah, if you do it the easy way, which I should do. Okay, so this one's the one which you're actually thinking about, like actual quasi application, I guess. So you have these exponential random variables, the cars. So I've got x is, let's see, aj and mj. So x is, I guess, going to be aj, and y will be mj. That is, the amount of time it takes aj's car to be fixed will be x. The amount of time for mj is going to be y. And since these are both exponential random variables with, it says rate 1. I don't know why it doesn't say lambda 1 or mean 1, but whatever. I'm going to use just 1 for lambda. So you get these two for our nice density functions, and then since these are independent, there's the density function for the joint density function. That's not really written correctly, is it? We'll get rid of that. Sorry, it's in the notation. It's correct. Yeah, that's better. So I didn't finish this, but I wanted to sort of identify what we're going to be doing. So the first question is, if AJ brings his car in at time t, I think I need to switch these, and then MJ brings her car in, oh, sorry, AJ brings his car in at time 0, MJ brings his car in at time t, we want to know the probability that MJ's car is ready before AJ's car. So let's see, MJ is X, AJ is Y. So if AJ's car plus T, whatever T is less than or is greater than MJ, which is Y. There, that's what we're looking for. The only thing that's irritating about this is that we're not told what T is. Why can't they just let us know, right? Well, I guess that now we have a formula if we do this. So, but do you understand, first of all, do you understand what's going on? You've got the two cars. One of them shows up right now. One of them shows up half an hour later or 20 minutes later or 2 hours later. I don't know. But it shows up sometime later. And we want to know what's the probability that the one that came in second is finished before the one that was here a long time ago. So that's the deal. So that's the way I've got this set up. This is the late car. So, oh, wait a minute. Whoa. I don't think I have this set up right. Hold on a second. This is less than this. Hold on a second. We want, just a minute. Here, I better draw. Let me draw what's going on. How about this? Okay, so this is X. This is Y. So we want the amount of time. I've got it now. This should be minus. Okay, let me explain. Yeah, I think I had my equation correct the first time, and then I kept changing it around. And now I've got a different but equivalent equation. So let's think about this for a minute. this is MJ's car. We want MJ's car to take less than AJ's car minus the time delay. So in other words, let's just think about some scenarios. MJ has to take a small amount of time, like half an hour, to get her car done, and AJ has to take a long time to account for the fact that MJ showed up late to the appointment. So you have MJ is less than whatever, like let's say that AJ's car takes 2 hours and MJ is an hour late. Then MJ better take less than an hour to beat AJ out the door. I think I got it. But anyone else? I mean, it's confusing, isn't it? You know, because we don't know what T is. But if you pick a number for T and just think about like, okay, so AJ drops his car off, and then some time elapses, and then MJ does, and we want MJ to finish before AJ, so that means MJ's car has to take less than the AJ minus some T. So AJ has to take a long time, in other words. So maybe it would be better to write it the way I had it originally. I think I had something like this. Y plus T is less than X. There, those are equivalent. So, okay, so let's actually do this. So Y plus T is less than X. Actually, I like this better, don't I? The first one. Now that I've got them both there, this one looks better. Okay, so Y is less than X minus T. That's this line right here. So there's T, Y equals X minus T. And so essentially, I'm going to be doing this probability. All of this, the stuff I've shaded purple, Y is less than X minus T. So here's AJ's car. MJ takes a smaller amount of time than AJ, but you have the T, the delay involved. Okay, so now I can do this. Let me just set it up, and then we'll move to the second one. So this one would be this double integral. So let's see, x, dx, dy, dx. Let me get rid of the extra d. Okay, so I'm going to draw my little rectangle like this. Notice that the y values start at 0, end at x minus t. It goes from 0 to y equals x minus t. X goes from t to infinity because you're starting here and you're going, well, it could take forever. Sometimes it feels that way when your car is being repaired. You call them up and, yeah, it's going to be another week. Okay. So then we'll do our joint density function, e to the negative x times e to the negative y. And that should work out. It's going to be a little bit of annoying because of this upper limit. You're going to, oh no, that's not going to be too annoying. No, that's not bad. That won't be so bad. So we could do this one if we need to, but I'm going to get the other one set up. But that's the setup. So see if there's any questions. That was part A. Or complaints. Maybe you don't believe me, which is fine. Okay, let's try part B. We want to know the probability that, so here, this one's much more straightforward because there's no t involved. So both cars are brought in at time 0, and the mechanic works on one of the cars, then the other car. So basically, I just want to know what's the probability, and we want to know what the chances that both cars are done before time 2. So I just want to know what's the chances that x plus y is less than 2, because we're going to do x first, and then we're going to do y. So that's just that. That's not bad. It's also going to be a little bit annoying because you end up with this as your sort of region. Here's x, here's y. So this is 2. This is 2. And this is x plus, whoops, parentheses should be over there. So this is x plus y equals 2. Or another way of writing that is y is equal to 2 minus x. So you're interested in that. So the way you would write this region is this. So x goes from 0 to 2, y goes from 0 to y equals 2 minus x. And then you've got this business again. So it won't be terrible. This one, at least you have a number that you'll get. But you can notice that this line is the event that the cars take a total of 2 hours. So for example, if x is equal to 2 and y is 0, what would that mean? It would be AJ's car took 2 hours, MJ's car was instantaneous. They looked at it and said, it's fixed. You know, and this happens to me when my wife will bring me her computer. I can't work it out. I'll be like, it's working now. Like, I don't have to touch it. I don't know why that is the case. It's like I've got this Jedi power. But anyway, that would be that. And here you've got 1 and 1, and so on. And anything down here, of course, the total is less than 2, so you're in good shape. All right, so any questions about that? I could do the double integral if you really want me to, but I don't know that we need to. So, we don't want to? We don't need to. We don't care. Okay, it's fine. All right, so let's go ahead and, yeah, why don't we give it a go? Here, let's see, is this one painful? This one's not painful. Yeah. Oh yeah, this one's super easy. In fact, it's so easy that you could answer part B doing no work whatsoever if you use the Sarah-Marhefka rule. So, but you can't get away with that on part A, although part A is pretty easy. So we'll give it a go. Hopefully this is correct. I will double check after I pass this around that the math works out. There we go.
That's one.
You need an extra one?
No.
Well, I only counted 3. I was ignoring this. I'm sorry, Nolan.
That's okay.
You're important. You're an important person. All right. Let's see. I've got this up here for those watching from home. I'm going to double check my math, make sure that's the right density function. Manage attendance. Oops. Find this thing. All right, hopefully you're coming on the home stretch. I'll get your homework first. So, we'll stack one. Well, I only bring it once in a while, so it keeps piling up. The homework in my little file folder. Nice, excellent. Yes. I'm not rushing. I'm not. The more you write, the more you have to read. Yeah. Oh, explain why. Yes, that was a mistake. Because I explained this a mathematical sentence. And this person did as well. Some people wrote actual sentences in English. Okay. Good. Works. That's something. So is that pocket square built in?
Yeah. Pockets are also good.
Yeah, oh yeah, well, you probably could take a seam ripper. That's the thing is, so I just open up all of my pockets. Because I like having the extra storage. It's like cargo shorts. Nice.
You set up for you.
I can tell it's going to be good. Oh,
Yeah.
Oh, it's looking good. Yeah. Very good. Good job. And you're actually surprisingly close. Yeah, that's good. You did it. You just didn't label it. It's perfect. You got it? Okay. Okay. All right. Is that it? Is anyone else holding out on me? Okay. Where's my stapler? There it is. I moved it for some reason. Okay. Let's see what I did. Hopefully I got it right. So the first thing to get the density, joint marginal density functions, the first one was the integral over the values of y. So you just treat the x as if it's constant. You got that integral, and you get 1/2 x. Nice job. I saw a lot of 1/2 x's, and then 2/9 y, or 4/18 if you didn't want to cancel out 2. But anyway, so it's just the same thing. You're integrating over the x's instead of the y's. You're doing great. And then why is this? Why are they independent? So I saw various sentences, but I just did this. I was like, yes, because there it is. The product of the two density marginal densities is equal to this. Someone said it's factorable. Okay, you can factor whatever. So good enough. All right, so today we're going to be taking a little step back from the probability stuff and take a look at some correlation, just to remind you of this thing that you did back in statistics class. It might have been a decade, no, not a decade, 4 years ago. Some of you had statistics back in high school, and you're like, yeah, I haven't had it in 4 years. Well, let's remind you of what correlation is. Well, do you know what correlation is? What does that mean? We got two variables, right? You got two variables, and we want to know what does it mean for two things to be correlated. So correlation, it's a word, this correlation, it means joint association. That's the word correlation. And one of the things that in statistics class that we like to say, and I know the psychologists love this, this phrase, is that correlation is not causation. Just because two things are correlated doesn't mean that the one causes the other. The story that I always tell my statistics class is this fable or myth of an emperor who was studying the relationship between disease in his empire and the presence of doctors. And he found out that in the cities that had the most disease, he also found there were the most doctors. And so he realized it was the doctors causing the disease and had all the doctors in the empire executed. Of course, that's ridiculous, isn't it? Because it's not the doctors causing the disease. There might be a correlation between having doctors and having disease, but it's probably the other way around. It's probably the disease that's causing the doctors to go, because that's where you would want to be if you're a doctor. It's somewhere where you can help people. Anyway, so like I said, this is most of this stuff is what we're doing is what I show my statistics students. So today we're just going to touch the tip of where correlation relates to probability. But for now, I just wanted to remind you about the correlation so that on Monday we can deal with covariance, which is part of correlation. Anyway, if you have two things that are correlated, then one of these things is true. Either A causes B, B causes A, or something else causes A or B. And I know we've been focusing so much on probability, we haven't talked about statistics. But statistics is just applied probability. It really is. Like when you compute a p-value, that's what we're going to be doing the last week after Thanksgiving, is talking about how do we compute p-values? What does that even mean in the context of statistics? So probability is really just the tools that are used in statistics class. So anyway, so this is kind of maybe a breath of fresh air today. Something else is causing the other, both of them. Good example of this is if you measure your shoe size and you measure your height, you'll find that there's a correlation between shoe size and height. So is your height causing your shoe size, or is your shoe size causing your height, or is it probably that there's something else? Specifically, you have genes that make your bones grow bigger than other people, and so that's causing them both to be whatever size it is. So speaking of shoe size and height, let's take a look. Let's skip ahead to this. Here we are. Yeah, shoe size and height. So, wow, it all showed up at once. So I have here some rounded numbers because I didn't want to have to deal with weird decimals. But here are the female heights in America. Average is 64 inches. Standard deviation is 3 inches. Average height of men in America is 69 inches. By the way, that's only true for all men in America. College-age men, the average height is, I think, 71, because we shrink as we get older. But anyway, and the standard deviation is 3. Same thing with women. It's a little higher for college-age women, but let's just use these. It's easier. I looked up the shoe size. Average shoe size, once again, I've kind of rounded a bit so that the numbers are a little easier to work with. My average shoe size for men is 10.5. Average shoe size for women is 8.5. And I realize these are on different scales, but I didn't want to make you convert to European shoe size, even though you have a European or maybe a global book. Most of us probably, well, I know my European shoe size, 47. You probably might not, I don't know. You're probably a 42 if you're a female, 41, I don't know, 40. But whatever, we can use these. So here's the deal, and I promise we're going to get back to correlation momentarily. Each of us, though, has a z-score for our height, and each of us has a z-score for the shoe size. Let me remind you what z-score is. I mean, you should know, because we just used it in the normal curve business. But here, I'll go ahead and do mine. So my height, just here, I'll do my height. So my z-score for my height is going to be my height minus the mean over the standard deviation. So I've got 1.333. Do the same thing for your shoe size. I will do it down here. So this is my height. And this is shoe. So you're going to do the same thing. Everyone gets to do their own. So you don't do mine, do your own. on, erase. There we are. All right, so everyone's got their shoe size and their height, their z-scores. Now here's the interesting thing. Some of you are like me. I've got 2 positive z-scores. So that means that I'm taller than average and my feet are bigger than average. By the way, I should say that this was not always my shoe size. One of the phenomena that occurs when you get older is you get shorter. And honestly, I'm not 73 inches anymore. I bet you I'm closer to 72. But I just can't bring myself to shrink down to 72 when I do this. So I'm going to leave it at 73. But anyway, my feet got bigger, oddly enough. I used to be a 12 in college, and then I was like, 12 and a half is more comfortable. Now I find that 13 is more comfortable. You shouldn't be, you should wear what feels good. I don't know if the shoes are getting smaller or if my feet are getting bigger, but whatever is happening is fine. So I've got 2.5 over 2, which is 1.25. So like I said, I'm both positive numbers, 2 positive numbers. Some of you are probably both negative numbers. I don't want to call anyone out because not what I'm going to do. But if you are shorter than normal, or not normal, sorry, shorter than average, and your feet are smaller than average, which would make sense if you're shorter than average, your probably feet are smaller than average, then 2 negative numbers, right? 2 negatives?
Would be like 0.
Awesome. That means you're perfect.
Okay.
Yeah. I love it. Do you have 0, 0?
I go 1, 0.
Oh, okay. It's 1, 0. Well, almost perfect. I was saying 0, 0, then you're right there at the mean. Perfect. Average, right? Anyway, so you've got your 2 numbers. The thing I'm curious about, and you don't have to volunteer if you don't want to, because I can just make someone up for this. But I'm curious if anyone has one of these positive and one of them negative. So that would be someone who's like shorter than average, but has larger than average feet, or vice versa. You do? Amazing. Okay, so you're like, you've got a positive and a negative. That's incredible. So that's unusual. It's very unusual because most of the time you have people, if you're taller, you have bigger feet. If you're shorter, you have smaller feet. So Sarah's unusual, which means she's special. We all knew that anyway. But anyway, we're all special, right? You all got your own comparison. But the point I'm trying to make is that in general, most of the time, you're either both positive or both negative. And the reason that's important is because the next step is we're going to multiply these things together. And if you multiply 2 positive numbers together, you get a positive number. If you multiply 2 negatives together, you get a positive number. The only time you get negative is if you're special and you have a positive and a negative, then you'll have a negative when you multiply them together. So here's mine, just so you can see. Let's see, I'm going to have to do this as fractions. So I have 4/3 for my height z-score. Whoops, go back. Go, no, go. Where is it? Oh, darn. I lost my place. There it is. Okay. So there's 4/3 for my height, and then it was 5/4. 5/4. Multiply those together, and I have 5/3. And that's my product of z-scores. So here's the deal. If we were to, I'm not going to do this, but if we were to take all of our products, so I've got 5/3. I don't know, Nolan has 0, which is interesting in itself because he's exactly average in one of his measurements, but a little above average in the other one. So that's fascinating. So anyway, if we all took all of our products, so I've got 5/3, Nolan has 0. What was yours, Sarah?
What was my number?
Your product.
-0.335.
Okay, -0.335. So she's -0.335, 0. I've got 1.66. You've all got yours. We take them all those products, and add them all together, average them. What we'll get is the correlation coefficient for height and shoe size. So this, no, it's all there now. There, I'll just, there. That is it right there. So correlation, You remember correlation back in, maybe you do, maybe you don't, back in statistics? Correlation coefficient is just the sum of all of our z-score products divided by n. That's it. So there you go. So that's the correlation coefficient. That's impractical, though, in general, to do that. Because what that requires to do this, to use this formula, what that requires is that we each compute our z-scores for 2 separate measurements and then average the products all. That takes a lot of time. It's a lot of effort. But it's interesting that that's the way it is. There's a much easier way that I'm going to show you here in just a minute. And the easier way is to do what's called a covariance. Eventually, we'll get to that. But I just want to introduce this to remind you what this is. So Pearson's R, also known as the correlation coefficient. I know there's a bunch of formulas here. I just took this directly from one of my stats courses. So this is z-score for the x-coordinate, z-score for the y-coordinate. There's the correlation coefficient there. So that, even though that's correct and easy to understand, it's hard to compute. This is the way math is often, statistics especially, is you have something that's easy to understand. It's easy to imagine this. You can imagine us all computing our z-scores, we just did. You can imagine us multiplying them together. You could imagine me collecting all those numbers together and averaging them. I could do it. I'm not going to, but I could. So the easier way to actually compute it, but harder to understand, is this. Now you might wonder, where in the world did this come from? Well, this came from taking the formulas for the z-scores, plugging them in here, and doing a whole bunch of algebra. And you end up with this nasty thing. Now that's not even exactly what we're going to use next week, but it's closer. This is much closer. M sub x is the mean of the x's. This is not the notation we'll use next week when we get to the actual R book. I've stolen this from the stats book, but you can understand what this is. So this is M sub x, M sub y is the mean of the y's. You know what these are, standard deviations. We end up with this weird correction. That'll go away when we do this for our theoretical probabilities. This n minus 1 is a correction factor because we have sample standard deviations that we won't have to worry about in the future. But I guess I'm just trying to point out that something that's relatively easy to understand can be rewritten in a way that's easier to compute but harder to understand. And it's that computation that we're going to be using. So in general, and what's going to happen, is there someone back there now? What's going to happen is that we're going to take this stuff. So let's just take this right here just for a minute. Take that and talk about the top there. The top. So these things, the things on the right, that's the expected value of x, the mean of the x's, and the expected value of the y's, the mean of the y's. That's what those are. And those come directly from the z-score formula. And right there is the mean of the x, the mean of the y's. So doing some algebra, you can sort this out. But that's what those are. Now this here, the thing on the left in that red box, that's the one that's a little bit more confusing. What is that? Well, what that is what you're doing is you're taking your x, your height, and your y, your shoe size, and you're multiplying it together, and we're going to do the average of everyone's height times their shoe size, which, you know, what in the world is that? Well, mathematically, we can write this down using our notation from probability. It would be this. It's the expected value of x times y. So this ends up being an important thing when we're talking about correlation. So this thing is what we call covariance. The covariance of x and y is equal to this. So when we do this for real on Monday, you're going to remember that covariance, it's just a measure or a tool that we use to come up with correlation. So all of these formulas, I'll put these back here, like this one. I do this, in fact, I will be using this actual slide in my stats class next week. So next Monday, I don't know if it'll be Monday now that I think of it. It might be the after break. Yeah, we're a little behind. Something happened. But anyway, so it might be the Monday after break that we get to this formula. But that's the exact formula that we have. It's a correlation. And the correlation is made up of covariance divided by a couple of standard deviations. Same exact formula, just looks a little bit different in our probability land. Okay, before we finish, I have a few more things to show you because I thought it would be fun to see this. So correlation, just a couple other reminders. So a few years back, actually I did this semester, didn't I? I made a survey of, I had these questions that some of you did to get bonus points. And in the survey, there were questions like, how much money do you have? How many classes are you taking? And then I had questions about like, when was Taylor Swift's 1989 album? When was it? Some of you remember, maybe not. Anyway, so I had questions like that. Anyway, a couple of years ago, I had a survey that was similar, but I made a mistake, and I had two questions that were almost identical. I'll show you those in a minute, but before I do, let me just show you a typical scatter plot of, like when you're comparing two exams. These are the same class. Here's exam 1, exam 3. And you would imagine that the higher grades you have on exam 1, the higher your grade will be exam 3. So there's a positive correlation between exam 1 and exam 3. I like to tell my stat students that you can see there's a positive correlation if it looks like you took a shotgun and you shot the screen at an angle. And so there's this spray that happens. And things are spread out, but it's generally a trend going upward. So there's a correlation here. It's not a very strong correlation. Anyway, getting back to that survey a couple of years ago that I made a mistake and had two of basically the same question. Here are the two questions. Question number 1, what year was Martin Luther King assassinated? And then question number 2, yeah, you could do this yourselves if you want to guess. So you could write down the year you think Martin Luther King Jr. was assassinated. And then question number 2 was, what year did Martin Luther King Jr. die? I know. You would think that, wouldn't you, Nolan? But not everyone thought that. So here's the graph that I got. So I guess I was kind of happy that I made this mistake. I didn't mean to. Yes, you're right. It should be the same. Yeah, right? Kind of makes, oh wait, you got two different years?
No.
Okay, we're coming back to you in a minute. But anyway, yeah, you would expect it to, assassinate, die. Isn't it basically the same thing? I don't know. But anyway, so I've got the graph. I was happy to have this because this correlation is like maybe a 0.4 or 0.5, not a very strong correlation. Things are spread out, so it's not a nice solid. I got almost a perfect 1 correlation. 1 means that we're all lined up in a row. It doesn't mean that the slope is 1. It just means everything's lined up in a row. So correlation doesn't tell you the slope. It does tell you if you're going up or down, but it doesn't tell you whether it's steep or shallow. Here, let me show you the graph. So here's the graph. Notice everyone is pretty much on that line. They're like, Martin Luther King Jr., he was assassinated in 1950 and he died in 1950. That's what you would expect. But you have a few people, little aberrations here, like this person here. That person thought that, I don't know what they're thinking. I guess they think, oh, MLK he died in 1950, but he was assassinainated in 1972, which I guess maybe assassination is like being like elected a saint, like sainthood. Maybe they thought, I don't know. Like they're like, oh yeah, he's being elevated to a saint. And then you have a few other people. Now these people I actually understand a little bit more. Like the people below here, this person, they thought that Martin Luther King Jr. was assassinated in 1955 but died in 1962, which makes a little bit more sense because, like, let's say he got shot in 1955, but he lingered a little bit until 1955 and died in 1962. So, but most of them said it's the same, right? So the right answer, by the way, is that he was both died and he was assassinated in 1968. So if you pick 1968, you win. And that's that. Let's see, what else we got here? This one's great. This is amazing. So here, and this still applies today. It's incredible. So I don't know, if you had me for statistics, then you might know this one. So can you find Ukraine? Ukraine's been in the news lately. Do you know where Ukraine is? Just, you can use your eye. Here's the interesting thing. Back during the first Ukraine conflict, this would have been about 12 or 13 years ago, when Russia invaded Crimea, and Crimea, the Crimean Peninsula, and there was a big conflict then. This group of researchers showed this map to people and said, click. So you're supposed to click, where do you think Ukraine is? Then, after they clicked, they asked them, on a scale of like 1 to 10, how important is it for the U.S. to join the conflict and go destroy the Russians or whatever? I don't know. Like how much do you want us to go to war, basically? So, have you got it? Do you know where Ukraine is? Let me show you, just in case. There it is. Is that where you got? You got it? I know, it would be a lot easier. It would be a lot easier if this was colored blue, because the Black Sea here, and then you'd see the Crimean Peninsula there. But yeah, there's Ukraine. This is Russia, obviously. So you know it's going to be one of these blobs over here. You just orient yourself with the Black Sea, and then you'll be good. But anyway, there it is. Now here's the cool thing or I don't know if it's cool or if it's really scary about this study. I've got the reference here, and this will be the last thing. Don't worry. Let me show you where everyone clicked. So this is, 500 people or so. Here's all the clicks. Ready? Now, I mean, you got quite a few people who thought Ukraine was where it belongs, but there were a few people who thought that Ukraine was like, what is this, in Kansas? Maybe they were thinking of Ukraine, like there are some cities named, weird things like Rome. There's a Rome in New York State. But now here's the correlation. So I got correlation here. Here it is. This is direct from the paper, the further our respondents thought Ukraine was from its actual location, the more they wanted the U.S. to intervene militarily. So if you're really stupid or you don't know anything about geographic stuff, then apparently you want to. Yeah, and all of these are I have that highlighted for my stats students because it's exciting to see, statistically significant written in a paper there. But so there it is. So now there's Ukraine, and you probably, if you knew where it was, you probably were less likely to want to go into war. So there it is. Okay, so what are we doing? On Monday, we will do covariance for real, and that formula that we had, you will see it pop up. That formula. It's going to pop up. It's easy. It's not bad. Trust me. Then, let's see. Then the week after Thanksgiving, so then we don't have any homework for Monday. That's the good news. And then for the week after Thanksgiving, we're going to do probabilities that are related to statistics, since this is kind of a springboard to statistics. So we'll go back and do some easy probability again. Hopefully that last week will be less painful than this past week has been. It's been painful for me as well. So there it is. I'm going to stop the recording in case you want to come chat. Otherwise, I hope you have a great weekend.